Um, all right, so Todd asked me to talk about blue carbon as it relates specifically to eelgrass habitat and habitat restoration, and then more generally also to talk a little bit about some of the caveats regarding blue carbon accounting and methodologies in general. So I'll start with eelgrass specifically, and then talk more generally toward the end of the presentation uh, about some of these caveats that apply to all different kinds of habitats. Most of the work and slides I'm going to show today are actually the collective work of my grad students and other colleagues, including Laura and Chris, who we've been working together for quite some time on bluegrass habitat. I mean, on blue carbon and eelgrass habitat and other habitats as well. So the credit goes to them, and I'll likely take the blame for any errors of fact that I utter today. Okay. So if you think about uh, uh, blue carbon. I mean, we've known for a long time that wetland habitats sequester organic matter and carbon. I mean, really by definition, an organic soil is a wetland soil. The term blue carbon was only coined, some 15 years ago or so. And if we only think about eelgrass blue carbon, I think we can identify three distinct errors. The first being this era of initial enthusiasm, and I think about that from about 2010 to 2018. Then after that, at least for the Pacific Northwest, there was this era of data collection and synthesis, 2018 to 2022, and it's still going on. And now, currently, we've refined our expectations based upon the data that we have collected. And so, if you think about this first era of enthusiasm, I think this was driven in optimism, and perhaps over optimism was driven by a few different things. One is many of the early estimates about blue carbon and eelgrass came from not from our habitats here in the Pacific Northwest, but from global estimates, including species like Posidonia that don't have the same morphologies as our eelgrass does, and I'll speak to that a little bit more a little bit later. Second is, well, just look at this picture here. This is many of you will recognize Padilla Bay on a low tide, exposing 8,000 acres of verdant, productive eelgrass, the largest contiguous eelgrass meadow on the West Coast. I mean, you could not help but be optimistic about the carbon that's being sequestered in the system when you just look at a picture like this. Another issue is that sometimes we confound carbon stocks, how much is there, looking at this meadow right here, for example, and carbon accumulation is, how much is actually of that carbon is actually being sequestered and stored long term in the sediments. All right. So the second era of data synthesis and analysis happened very recently and is still happening. And there wasn't really a lot of data about blue carbon stocks and blue carbon accumulation before this second era here. And I think this era is best represented by this seminal paper. It came out in 2020. It's kind of hard to think about a paper being seminal that's only 4 or 5 years old, but there really wasn't much to look at before this. Um, it's well cited now, even in its young stage here, and it was co-authored primarily by four younger graduate students at the time: Carolyn Prentice at Simon Fraser, Katrina Poppy, and Mira Lutz at Western, and Aaron Murray at UW. And so they took it upon themselves to quantify, and they found each other at various conferences and got together and collaborated. It was really quite amazing. And they took it upon themselves to quantify blue carbon sequestration rates in the Pacific Northwest eelgrass meadows. And most of the data um, that we have now uh, comes from this study, data that they actually collected, and some of it that they were able to mine from other sources. But really, most of this was data that they collected and analyzed themselves. And so this is one of the by the way, I'll post a link to this paper in the chat after my talk in case you want to go ahead and take a look at it. So this is one of the graphs from their paper, and this is, on the x-axis is carbon accumulation rates in grams per meter squared per year for a bunch of different sites in the Pacific Northwest, and compared to that global average. And so you can see this global average at the top. This speaks to that era of initial enthusiasm when the measurements that we did have were coming from these tropical and subtropical species with very elaborate root structures that are lignified, and we just don't have the same kind of species here. And if you look for our coasts, BC and Washington, the rate of organic matter accumulation is an order of magnitude less than these global averages. Okay, this is another study, and actually Laura Brophy before just showed a similar slide. I think it's the same data, just a different picture of it here. So this is carbon accumulation and wetland types, and there's two things I want you to see here. One is, so eelgrass carbon sequestration is quite low compared to other habitats like swamps, reference marshes, or stored marshes, and Laura spoke to this. But here, I'm going to talk about this a little bit more too, is that there's really no significant difference between the carbon in eelgrass beds and the adjacent tide flats, mud flats that are found a little bit upslope from many eelgrass beds. In fact, Prentice's 2020 paper, they did isotopic analysis of the sediments below eelgrass beds, and they found that actually most of the carbon in the sediments wasn't coming from the eelgrass itself, but rather from riverine sources, or it was macroalgae, benthic algae, and diatoms. So really the amount of carbon stored and sequestered in the eelgrass beds, not much different than the tide flats. Okay. I don't know why I'm not advancing here. Okay, so let's get down to why why don't eelgrass carbon why aren't they high in the Pacific Northwest? And so I want to talk a little bit about some of the mechanisms of why we may see that is the case. And so first of all, and Laura spoke to this a little bit, we need to think about carbon accumulation. And by the way, I will use carbon accumulation and carbon sequestration interchangeably. They really mean the same thing. So how much carbon is stored in the sediments per year, because that's what blue carbon is all about. And it's a function of two things. One is carbon density, how much organic matter is in the sediments, and how much of that organic matter is carbon. Typically, it's around 30 to 40% of the organic matter is carbon, and that's fairly easy to measure. Take a core, bring it back to the lab, you can figure that out. And then the other thing is, what is the accumulation rate? What is the sedimentation rate in centimeters per year? Actually, I see that accumulation rate should really be accretion rate. What is the accretion rate in centimeters per year of the sediments? This is harder to figure out, the accretion rate in centimeters per year, and I'm going to talk about that later. But a spoiler alert, in eelgrass beds in the Pacific Northwest, both the carbon densities and the accretion rates here, not accumulation rates, that's an error there that I wrote, are both rather low. And as Laura pointed out, I don't know if you caught what she said, but it's absolutely true, and I'll show you a slide in a second, is that around here, our carbon accumulation is really driven by the accretion rates more than the carbon density. But I'll speak to both of those in a second here. So this is a slide. I know Laura had it in there in her presentation earlier. She took it out so that I could show it. Thank you for that, Laura. So I didn't get scooped there. But this is also from the Prentice paper. But here's on the y-axis is carbon accumulation rates, and on the x-axis is carbon density. And on this slide here, we have accretion rates versus carbon accumulation rates. And you see, a very clear trend of accretion rates versus carbon accumulation. And this is data collected from Pacific Northwest estuaries. I mean, if you getting an R squared of 0.78 in ecological data, I mean, that's amazing. If any of you attempted to discern patterns from regression equations, this is quite remarkable. I would even say this is quite remarkable. I can see that line, but you can see that the relationship between carbon sequestration and carbon density is not there compared to accretion rates. So. Um, So let's talk about specifically, why are these accretion rates low in eelgrass beds? Well, really, it's almost by definition, as I mentioned in the previous slides. You know, uh, Well, I didn't mention this. I'll mention it now. Eelgrass thrives in regions where suspended sediment concentrations and subsequent settling and accretion of those sediments is low, but light penetration is high. There's kind of this conflict here. If you want high carbon sequestration, you want high sedimentation. But if you have high sedimentation, you have turbidity and you don't have much eelgrass growth. And to illustrate this point, I'm going to show you some data here. This is from Padilla Bay, where we set up elevation monitoring stations back in 2002, and we've been monitoring them ever since. And these little green dots here are where our monitoring stations are. So we've been able to track how elevation has changed in these eelgrass beds since 2002. We've also done some modeling. Oh, We've also done some modeling, and this is our version of the warmer model, which Laura spoke to briefly. And really, this is a dynamical. Can't get into the details of it here, but this is a dynamical sediment core model of eelgrass meadows. It uses data from our monitoring network for modeling initialization, carbon, and validation to understand and predict how the effects of changing sediment concentrations and sea levels on eelgrass productivity, elevation, organic matter accumulation, blue carbon really in Padilla Bay. So we had this um, coupled field study and modeling study to one of the things that we could do with it, although we didn't establish this network or build this a model initially to look at blue carbon. We were looking at sediment accumulation, and from there it's a small leap to blue carbon. And some of the things that we have found is that here is elevation change relative to the initial. From this graph goes from 2002 to 2018 for all those stations in Padilla Bay. And what you can see here is that generally all of these sites are losing elevation, slowly losing elevation. So they're not even actually accumulating sediments. They're losing sediments and organic matter and blue carbon. 2-decade record of elevation loss here of about 1.4 millimeters per year. Additionally, our models showed that in order to even maintain elevation with the rates of sea level rise, we would need to see a suspended sediment concentration, and some of those sediments then settle and become part of the sequestered sediments of around 15 milligrams per liter. And currently in Padilla Bay, what we actually see is TSS concentrations of around 3.93 to 4 milligrams per liter. Again, pointing to why eelgrass is so productive there. So, and 15 milligrams per liter is actually kind of right at the limit of what Zostra meadows around here can tolerate in terms of turbidity with regards to light penetration and photosynthesis. So again, we have this dichotomy between maximizing blue carbon and max sequestration, and also at the same time um, having a thriving bed of eelgrass. So the two don't unfortunately match up. Okay, and this is just as an aside here. This really makes sense. I mean, prior to levees and dikes, the Padilla Bay was part of the Skagit system, and there was, a hydrologic coupling that doesn't exist anymore. Padilla Bay is now essentially, uh, for all intents and purposes, uncoupled from the Skagit system. Um, but that's likely why eelgrass is thriving there, because there is not heavy sedimentation. There's low suspended sediment, TSS, and good photosynthesis. So, all right, next. Carbon density is also low, um, in although the link isn't as high, with regards to the correlation between carbon density and blue carbon accumulation. Carbon density is also low, in eelgrass meadows, in the Pacific Northwest, and it's actually, just as an aside, it's also low, compared to marshes of the Southeast, for example, in other coastal habitats. So when you take a core, and this is a picture actually from an eelgrass meadow, this is typically what you see. There's a lot of sand, silts, and clays, and very little organic matter, in that core. And this is for several reasons, actually. Um, One is it's the structure of the eelgrass itself. I mean, if you've been out there looking at eelgrass, it has this shallow rhizome system, with very small roots. And the total penetration is really only a few centimeters into the sediments. So you don't have, these deep-rooted systems compared to some of the tropical and subtropical eelgrasses that have these highly lignified root systems that extend down, for 10, 15, or 20 centimeters. That's not typically what you see in our eelgrass beds. They're very shallow rooted. Second, this above ground biomass, which could be, when it senesces, could become incorporated in the sediments. That's a typical paradigm for what happens to some of the above ground biomass, is that it falls and becomes incorporated into the sediments and then sequestered, potentially as blue carbon. These leaves, as I think we all know, they're not lignified, resistant structures. I mean, here's again Padilla Bay on a low tide. They're very labile, and tend to decompose rather rapidly, as they compared to a stem from a sedge or a rush. So if you're thinking about long-term carbon sequestration, you have to have, rapid burial of organic matter, and you would also hope that this organic matter, was somewhat resistant to decomposition, and that's almost the opposite of what's happening in a eelgrass bed. And this is again from the Prentice paper. This is percent organic matter, carbon. Here's the global average again, 2.5% organic carbon. And then if we take a look at our systems here again, about half of that. As an interesting aside, in applying to all different types of coastal habitats, here in the Pacific Northwest, and especially around, here in the Salish Sea, our sediment organic matter is quite low, compared to what you might see in a southeastern, um, uh, Spartina marsh, for example, or even a mangrove marsh, where percent organic matters can be 10 or 15, or organic matter can be 30 or 40%, and half of that, or a little bit less, being carbon. So we don't have these organic rich, sediments like we might see in other parts of the world. We have, and that again, that goes a little bit back to what Laura mentioned earlier. So, we have a lot of sediment availability, uh, and that sediment typically is mineral, not organic. So, okay. Now I'm going to step aside from that for a little bit, and talk a little bit more about methodological restraints. And I'm going to talk specifically about, how do we measure rates of sediment accretion? And this question actually comes up quite a bit, for our lab, if a practitioner is wanting to incorporate blue carbon, uh, calculations into their restoration plan. They're mostly concerned about how do we measure that, and largely that's an issue of how do you measure rates of sediment accretion. That's the part of the equation that's difficult to get at. And unfortunately, there are several methodologies, but unfortunately, they all work the worst in eelgrass beds. It's the hardest type of system to get a handle on, in my opinion, with regards to sediment accretion rates. And I'll talk a little bit about all these. So there's three ways really, common ways to get a handle on accretion rates if you're considering blue carbon in any kind of habitat, not just eelgrass beds. You can look at horizon markers. You can take cores, or you can use surface elevation tables. And so I'm going to talk briefly about all three of these just to kind of give you, an idea about what you can use and what the problems with those are. So let's start off with horizon markers. So this is the easiest and the quickest and the cheapest, essentially, and many of you have probably heard about these or maybe even have done it yourself. You lay down some kind of marker, a feldspar clay, a powder onto the surface of marsh, and then you come back later, you take a simple plug, you look for that layer, you measure the sediment on top of it, easy to do, figure out how much of that is carbon, also easy to do, and you have a rate of carbon sequestration. You also have a rate of accretion. However, this is a short-term rate of accretion. Much of that organic matter and associated carbon has yet to decompose or compact. So this method greatly overestimates actual long-term rates of accretion, and that's what you need for proper blue carbon accounting. So this method is not appropriate for blue carbon accounting. Additionally, this is very hard to do in eelgrass beds because you might imagine on a mud flat or an eelgrass bed, tide coming in and out, in and out, in and out every day. You put down a feldspar layer, the next day it's gone. It washes away quite rapidly. This works better in a higher marsh that is occasionally inundated and has a lot of stems there to protect it. So, all right, next is the what I would call the gold standard, and this is taking a core and then calculating sediment accretion rates by down core lead-210 gamma emissions. And the advantages of this is that it is a rather quick method in terms of just going out there and taking a core. And you can figure out lots of things from that core: bulk density, organic matter. You can figure out carbon. And then using gamma ray spectrometry, you have to find a lab that can do that. You can calculate long-term accretion rates that way. So now, and the cores are you don't have to be sophisticated in the way you collect a core. We very commonly just a PVC pipe driven down. Only 50 centimeters is enough. You don't need to go way deep to do this. And so you can get a good estimate from just a core, a half a meter core, quite easily. So that's easy to do as well. Just another picture of taking a core in a shrub habitat here. So this method again is fairly straightforward. It's considered the gold standard, but the problems with this is that you need an accretionary sediment environment that's not affected by bioturbation. And unfortunately, these conditions are often not met in eelgrass beds where bioturbation is common. Additionally, if it's a restoration site that was perhaps an old pasture at some point, farmland, probably very disturbed, you need to have a site that's not doesn't have any kind of bioturbation. So I'm going to actually skip a slide here. I don't want to talk more about that. I can answer some questions if we need to later. So, and then the other methodology is the use of surface elevation tables. And this is the network in Padilla Bay, for example, uses surface elevation tables. And we call them sets. If you haven't heard of these, this is a portable leveling device attached to a permanent rod driven to the point of refusal in a marsh, and it provides a fixed and stable benchmark from which repeated measurements can be made to measure changes in elevation. I showed you a graph of one earlier, or the results. This is what they look like. in the field. This whole top part comes off. And you end up with lovely graphs like this, where you have elevation change over time. This is from Padilla Bay, and this is another way to estimate long-term rates of accretion. We actually have a network of these um, in the Salish Sea, the Puget Sound side of the Salish Sea. The first were established in Padilla Bay. There's over 100 of these now deployed in the Padilla Bay, Nisqually, Stillaguamish, Snohomish, Skagit, looking at about 70% of the current estuarine habitat in the Salish Sea. So some of the problems with this is that it takes some time and commitment to commit to a set network. It takes a little bit of money, and then you collect, unlike a core where you just take a core and get a result. It can take years to gather the data that you need. And again, unfortunately, it doesn't work that well in eelgrass beds where there is a lot of in mudflats where there's a lot of tidal movement and not a lot of protection. These devices themselves can cause scour, trap, macroalgae, and it can be a real mess in eelgrass beds. So it's difficult. Better in habitats like upland marsh or high marshes or low marshes where you have a lot of protection. So, all right. So just some other caveats to think about in general, and going back toward eelgrass, um, uh, and 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 Laura made reference to this, and so did Melissa. The size of eelgrass restoration projects are typically quite small in compared to other coastal restoration projects. So if you're thinking about this as a funding mechanism, you're really, you're not talking about large scale restoration like you might be thinking about with the mangrove, as Melissa talked about. And as she also mentioned, success is often quite low, less than 20%. There's also problems with additionality. And what I mean by that, in order to accrue carbon credits, you have to show that your project is increasing the baseline amount of carbon that's already there. You're increasing the sequestration rate. And if eelgrass beds don't have any more accretion than the tide flat adjacent to it, or and any more carbon accumulation, then it's going to be hard to find any additionality that way. And then finally, as I referred to before, eelgrass restoration best management practices with regards to sediment are in conflict with other coastal management habitat projects where in most habitat projects, you're trying to enhance sedimentation to grow marsh. And that's not actually a good practice for eelgrass beds when you want to try to reduce turbidity to promote eelgrass beds. So, all right. And then so take home messages. I left this when I had AI generate a beautiful slide, and they put a cactus here, which kind of cracked me up. I don't know why they did that, but I thought I would just leave it there because it's because of the absurdity of it. So take home messages. So carbon sequestration rates are low in the Pacific Northwest eelgrass meadows compared to other coastal habitats, and in some ways that's self-limiting because you're not going to find carbon where you're not going to find eelgrass where there's lots of sedimentation. Quantifying it is difficult. I talked about that. And due to the size of typical restoration sites, you're going to see limited success with additionality. Blue carbon sequestration as a funding mechanism is not likely a realistic solution with regards to eelgrass beds. And finally, I don't want to, eelgrass habitats provide many ecosystem goods and services, but compared to other coastal habitats, carbon sequestration is probably not high on the list. And I'll stop right there.
Thank you, John. That was excellent. We do have time for probably just one question. I've got one that came through the chat here. Why are sediments in the Pacific Northwest lower in organic content than mineral content as compared to Eastern US sediments?
Good question. I would think two reasons. One is that we just don't have the kind of plants that you in the morphology of these plants that you see like in the southeast. Like if you take Spartina, and we had some Spartina, but we eradicated all of it, which it is a good thing. But if you look at the structure of those plants, it's just these massive root structures that go down for a meter or two, well, that might be a little bit of exaggeration. Just a lot of below ground biomass. And we don't, and they also thrive in very low, low elevation, lower marsh areas. We just don't have an analogous plant like that here in the Pacific Northwest, that has that kind of below ground structure that grows at such a low elevation. So I think that's a big part of it. The other thing is we just have, you know, and part of it is a function of we just have a lot of sediment here, mineral sediments pouring into our estuaries, which is a great thing for habitat restoration. And if you're familiar with the issues that's happening in the Mississippi River Delta, they don't have enough sediments to rebuild their marshes, quite frankly, and so we just have these large inputs of mineral matter compared to organic matter.